All right, everybody, let's get started. Lecture 29. I mentioned in class, I think like last week, I said that there was that I wasn't going to be here next Wednesday. Well, next Wednesday is 2 days from now, so we do not have class on Wednesday. Okay, so I wanted to take a few moments and detail not just the logistics this week, but I started looking at just like where we're at in this class, and I thought it would be prudent to put together sort of a, hey, here it is, be all end all, this is what's going on between now and the end of the semester. Because like I said, the semester end is coming sooner rather than later. So I am giving you a homework assignment today, but it is due Friday, not because it is long or anything, but it's simply because we are just not going to be here on Wednesday. Now I told you that exam 2, I was probably going to have that graded between today or Wednesday. To be honest, I'll probably have it graded by Wednesday, but I'll just give it back to you on Friday when we come back. Okay. All the outstanding homework is graded, and homework 5.3 was today. That was the distributed load assignment and the truss centroid. Was that simple? Hopefully it was. Okay, did everybody get the code? All right, eyes up here because I have a feeling this is going to be the Instagram slide. Okay, so that everybody snaps a picture of. Okay, so this is our schedule between now and Thanksgiving break. Okay, and I'll talk a little bit about what we're going to do after Thanksgiving break, but just to sort of take stock of what's going on. So we're in week 11 right now, and we have week 11, 12, 13, 14, and then we go on break for Thanksgiving. We come back from Thanksgiving, we have a week 15, and then we have our final celebration. Okay, so let's take it week by week. Okay, so this week we're going to finish out Centroid. So we've got a lecture today and a lecture on Friday. Okay, we're actually kind of going to finish Centroids today, but there's a lingering topic which we're going to discuss called the moment of inertia, and we'll talk about that a little bit today and mainly on Friday. Okay, the following week, week 12, we're going to live in structural analysis land. I know that some of you are probably thinking, oh, Dr. Mike's a civil engineer, we got to do structural analysis. The main reason that we do structural analysis and statics is because the topic packages together a lot of the core principles of statics into classical engineering problems. So for example, we're going to learn how to analyze a truss. Well, in order to analyze a truss, you need to understand statics of particles, you need to understand rigid body systems, rigid body equilibrium, also the inherent assumptions behind how we perform a truss analysis hinges on our understanding of centroids. So that's just an example of where there's a lot packaged into the types of problems that we do. So they're really great exercises to enhance your understanding of statics. So we're going to do that. We're going to have 4 lectures on that. So 2 of them are on trusses and 2 of them are on beams. And then on week 13, we celebrate. So we have our exam review Wednesday, November 13th, and then we celebrate on Friday, November 15th. That didn't change in the syllabus. The only thing that changed is that we shifted lectures down a little bit. We only have 4 lectures in structural analysis instead of 5. Week 14, what we're going to do is we're going to have 2 lectures on friction. Okay, that's our final topic in statics. And then we're going to cancel class on Friday. Now, a little bit about this week 14. I am going to assign 1 homework on friction. I'm going to have it assigned Wednesday, and I'm going to have it due Friday, even though we don't have any class on Friday. And my main reason for that is this. I want you to have a break, a real break in this course. Okay? So I want this homework assignment submitted this week, so that during Thanksgiving break, do you know what you have to do for this class? Nothing, other than have some Thanksgiving dinner. I will also tell you that this is the last homework in Engineering 213. So what do we do when we come back during finals week? We're going to do a comprehensive class review. So mainly Monday and Wednesday, we're just going to go through housekeeping in the class and then do relevant example problems that week, and then Friday leave you all time to ask any back and forth questions on the exam. And that, ladies and gentlemen, is Engineering 213. Does that sound good? So again, so the key dates, I think, for you all, we do not have class on Wednesday. Exam review Wednesday, November 13th. Exam Friday, November 15th. We are canceling class the Friday before break. Sound good? Any questions? Okay. All right. So with that, let's go ahead and jump into our topic for today, which is sort of two topics. So what we're going to do today is we're going to discuss. Oh, by the way, everybody get the code? The QR code? Okay. So we're going to sort of do two topics today. The first topic is we're going to close out centroids, and then we're going to talk about moments of inertia. So centroids of a three-dimensional region are conceptually locating those is conceptually no different than locating the centroid of an area or the centroid of a group of lines. It's all kind of the same thing. It's just instead of dealing in terms of areas, we're dealing in terms of volumes. Now, one of the things about a three-dimensional centroid location is that we do still use two-dimensional references. So I'll give you an example. If I wanted to determine the location of a centroid of a, let's say, triangular prism, okay? So let's say I had a triangular prism that looks something like this, in three dimensions, and that's a right angle, right? So where is the centroid of this simple shape? Well, how do we get there? We go a third of the way up, and then maybe like halfway, and that's where the centroid is. Does that make sense? So even though it's a three-dimensional region, it's not like that none of these two-dimensional references are relevant. Okay. Now that's not to say this is enough. Okay. There are some geometries where in 3D we would need a separate reference. So first off, by the way, again, the pattern doesn't change. We're just integrating or summing in terms of volume, not in terms of areas or in terms of length. But the real thing I wanted to point out to you is maybe something like this. So for example, if you had, let's say, a hemisphere, okay? Maybe you have some geometry that has like a hemisphere on it. This is probably one of the most practical examples of where a 2D reference isn't going to be enough. Right, there's like, this isn't sort of a two-dimensional shape that's been extruded, to use the Engineering 102 terminology. So if you had a two-dimensional shape that's extruded, just find the centroid of that two-dimensional shape, and then halfway through the extrusion, there's your centroid. But for a revolution, maybe like a hemisphere or an ellipsoid revolution or something like that, the centroid isn't as simple to find, at least this way. And that's where these references come into play. I'm not going to use one of these today because I don't really think that's the challenge in locating the centroid in a three-dimensional body. If I'm going to occupy your time here in Engineering 213, I'd rather address what I think are the trip-ups that you're going to have, where you're going to have hiccups doing these types of problems. And the hiccups aren't, oh, well, now I need to use a new reference. You can Google this stuff. The hiccups are what I would call the overlap issue. And the overlap issue will become clear in this example. Okay, so I have here a three-dimensional part, and we're going to determine the location of the centroid. Now, I'm going to go ahead and tell you that we are not going to locate the X, Y, and Z, bless you, for the entire shape. What I'll do is I'll locate X, Y, and Z for each individual shape, and then for the purposes of demoing, we'll just pick one. I think I have my calculation set for the Z bar, and then you'll see what I mean. Like if you wanted to do X bar, if you wanted to do Y bar, it'd be all the same. So let's go ahead and jump right into the example just to sort of make the point, this overlap issue. And this example really does test my 3D art skills as much as possible. Okay, so what we're going to do here is we're going to break this up into simple shapes the same way that we have been doing problems. And I'm going to see if maybe on this master image right here, maybe I can kind of illustrate what we're going to do. So let's see. Maybe what we'll do is, let's use some color here. Okay. So the first thing that sort of jumps out at my mind is this sort of quarter circular region right here, if everybody kind of sees this. So this quarter circular region, like here's sort of the center point. So the center point is sort of like right there. And what we do is we jump out 2 inches and sort of revolve that way. So if I wanted to separate that maybe into a semicircular region, or a quarter circular region, I should say, I would say that this green line right there that sort of corresponds to that simple geometry. Does that make sense? Everybody with me on that? So if that's the case, I have this quarter circular region, and then I've got 2 holes, right? So I've got, well, I'll use red for those. I've got these right here. Which these right here would just be circular cylinders, right? So circle extruded, right? And then I've got the rectangular prism, if you were, the box, as it were, okay? Now, the big thing that you want to do is make sure that when you're defining the box that you're fully encompassing the geometry. One of the things that's really sometimes tricky on homework problems or exam problems is to say, well, I'm going to define the box that goes like that. Something like that. And the problem is that you're not accounting for this central little overlap region. So does the box need to go all the way to the end for this problem? Yes, it does. Okay. So what we'll do is we'll say that that's our box. So the box has to go the whole way across. Okay? So when we're looking at these individual geometries, we need to handle it that way. Does that make sense? Okay. So what I'm going to do, and by the way, I sort of cheated here because I made copies of the image over and over again because as we're drawing this out, I didn't want you to go, wait, I didn't get all the dimensions. But I still wanted to go on with the problem. Okay, so we're going to do this one shape at a time. And I'm going to move this up a little bit. And what we'll do is we'll say shape 1. We'll call this a rectangular prism, okay? So just to highlight that shape here on this sketch, what we're talking about is this, okay? So again, this is going to go into that intersection region, okay? So and so what I'll do is, remember that perspective stuff we used to do in Engineering 102 where you could see behind the object? There's the dashed line. Okay, so maybe what I'll do now is I'll isolate that box over here. Let's just look at that box, okay? All right, so by the way, the one thing I'll also point out is that point right there. Why am I highlighting that point in particular? What's so special about this point on the prism? Origin. That's the origin, right? So whenever we express our individual distances, we need to express it with respect to that point. Okay? So let's come up with some dimensions. Okay, so let's see. Let's see. What is, let's see, this dimension? What's that dimension? That's 2 inches. Now, it wasn't sort of explicitly given, but we know the radius of this this quarter circle is 2 inches. So we'll call this 2 inches right there. Okay. Let's see. Okay, what's that? 4.5 inches. And then the thickness. That's a 1/2 inch. So therefore, let's do volume first. Let's do the volume. I'll call it volume sub 1. Okay. So this is a box. So the volume of a box is just length, width, height, right? BHL or something like that. So we'll say right? So the 2 and the 1/2 are going to cancel each other out, and so that's going to be 4.5 cubic inches. Okay? Sound good? And then what I'm going to do is I'm going to say, okay, give me an X1, a Y1, and a Z1. Okay? And we're going to express those with respect to the origin. Okay? Now, by the way, let's make sure we're all clear, right? The centroid of this simple shape is going to be like right there, right? In the middle of the box, right? In the center of the box. So here, this is the x-axis, right? So how far along the x-axis do I have to travel to get from the origin to the centroid? Along the x-axis. A 1/4 inch, right? Because that's that little thin dimension. That's this 1/2 inch. So we're only going half that. Okay? What about the y-axis? Right there. -1 inch. Because the y-axis is pointing up. We have to go down to get to the centroid. So this is -1 inch. And then along the z-axis is going to be what? 2.25. Okay. Is that okay? Does that make sense? Everybody okay with that? Okay. All right. All right. Any questions? Okay. So now we'll do shape 2. Okay. And this shape 2, I'm going to call this quarter circular region. Okay. And by the way, let me do me a favor. Let me drag this down because I have a feeling I'll need a little bit of space here. Let's go a little further. Okay. All right. So this is where bookkeeping is really important. Okay. So this is another sort of hiccup that you can get. Okay. So what we're talking about. Oh, what happened there? Sorry. We're talking about this region right here. Okay? Okay? Now, by the way, for a quarter circle, right? And I'll stick this here on the board. If you have a quarter circle, if you just have that, and you want to find this dimension here, or this dimension here, both of them are still 4r/3 pi, okay? the same thing for the semicircle. So I'll just stick that up here on the board for reference. But we got to be careful with our bookkeeping, okay? So, oh, this is going to be tough. Okay, bear with me. All right, so let's see. I'm going to draw this maybe kind of big. Maybe that'll save me. That's about the best you're going to get out of me. I am not drawing that again. Okay. Now, by the way, where is the... so hold on. Let's make sure we're all paying attention. So that's the origin, right? You're shaking your head no. Why?
Because it's based off the origin a
Half inch away. Exactly. So the origin is actually like right there. Does that make sense? Okay. Okay. That's important. Okay. That's important because when we start calculating our X and Y values and whatnot, X, Y, and Z values, we have to be cognizant that we're referencing these appropriately. Okay. So let's see what I can do here. Bear with me. Okay, so we've got... So by the way, let me just do this. R equals 2 inches. Okay. And then, wait, oh, wrong way. Both of these dimensions are going to be 4r over 3 pi, okay? And by the way, this thickness is 0.5 inches. Okay, and help me out. What is that dimension right there? This little dimension right here, from the origin to this little edge right here?
0.5.
Right here, that dimension right there is 0.5 inches. Okay. Okay. Let me do this. Do something like that. Okay. I'm not drawing anymore. I think I'm hitting my limit on my artistic abilities. Okay. Let's do what we did last time. Let's first off calculate a volume. Okay. So let's assume that this was a cylinder. How do you calculate the volume of a cylinder, right? So if it was a circular cylinder, we're going to have to do this problem here in a bit anyway. So you take the area times the height, right? So pi r squared times the height. But because this is a quarter cylinder, we're going to take pi r squared over 4 times the height, right? So this is going to be we'll call it times the thickness. Lower just a little bit. Does that make sense? So this is going to be okay. So how's this going to work out? So we have 4 squared over 4, and 4 is going to cancel, so half a pi. Half a pi is what, like 1.571? Is that fair? So what are we getting for these? Okay. Oh, I need a like that. And if you want to know why I draw a line through my Z's, tell me the difference between that Z and that 2. I can't do it. Okay. Okay, so let's start off. Let's do the easy one first. Let's do the Z-axis. How far is it from the origin to the centroid along the Z-axis? This way. Well, if it's a 1/2 inch thick, it's just going to be a quarter, right? 0.25. Maybe I'll put some space between these because I have a feeling I'm going to need it. Okay. Now the y-axis is going to be 4r over 3 pi. But is it positive or negative? Negative. Okay. And when you chug that out, you get something like negative 0.849. Something like that. Okay. But what about the x-axis? How do I do the x-axis? This is the one I really want you to pay attention to. So how do I get from the origin to the centroid of this shape along the x-axis?
0.5 plus 4 over 3 pi.
That's exactly right, because we have to go this way and then a bit, okay? So it's 0.5 plus 4r over 3 pi. 4r over 3 pi. Blech. And so it's just going to be like this. Okay. Goodness, that splashed on me. Sorry. All right, does that make sense? Everybody okay with that? Okay. So far, so good? Now go ahead and scroll. Okay. So the next thing that we have to do is these holes. Okay. And I'll call them cylindrical. Okay, so for these cylindrical holes, I'll drag this up a little bit. Okay, so we're talking about this and that. Okay. Now, first off, let's label these a bit. Okay. So we'll call this hole 3. Call that 4. Okay. I think at the beginning of the problem, yeah, the diameter of each hole is 1 inch. So we'll say, note we'll say the diameter is 1 inch, so the radius is a 1/2 inch. Okay. So let's package together as many calculations as we can. Both of these holes are going to have the same volume, right? They're going to have the same volume, so the volume is just going to be pi r squared times the thickness, right? Anybody have a problem with this calculation? It should be negative. Why is the volume negative? Because it's a hole. We are removing that material. Okay? So this is going to be that, or, so basically it's just going to be pi over 8. And I hope you'll permit that I can just tell you that's that. Okay? So far so good? Okay. So let's see what we can do. Okay, so we're going to have an x3, y3, z3, x4, y4, z4. Okay. Are these going to have the same x centroid along the x-axis? How far is it from the origin to the centroid along the x-axis? 0.25. Is that the same for both of them? Yes. So this is 0.25. 0.25. How about the y-axis? Is that going to be the same for both of them? Hold on.
Oh, wait, yes.
The y-axis is going to be the same. Everybody shaking their head. No, it's the z-axis that's different, right? So the y-axis is going to be -1, but it's the z that's different. What's the z going to be for? What's the z going to be for 3? Let's say for 3. What's the z going to be for 3?
-1.
Okay. All right.
1.5.
1. Oh. Why did you say 1.5? Because there's this. Ooh, see? Right here. So check this out. So like the axis goes like this way. There's, oh, that drawing was horrible. Bear with me. So keep in mind, let's draw the blue box. Keep in mind the blue box goes back some. What's that?
Because the 1/2 inch is coming from the thickness of the quarter circle.
Yeah, that's what I'm saying. Yeah,
Yeah.
that's what I'm saying. We've got to account for that part. Yeah, that's what I'm saying. So what I'm saying is that Z3 1.5. Does that make sense? Because we got to go back that way. Okay. So if this is 1.5, what's this one? 3.5. There we go. Does that make sense? Okay. If that makes sense, then if you permit me, the location of the actual calculations, the centroid calculations, it's sort of a breeze, right? All you need is the x, y, and z for each shape and the volume of each shape. So what I'm going to do is I'm only going to do one of them. So I'll say let's just consider z bar. Again, it's going to be the same for all of them. So what we're going to do is we're just going to do this. So okay, so we have 4 shapes. So I'm hoping that you find that this part's the boring part. Because all we've got to do is go back to our calculations and said, okay, this one, let's see, this was 2.25, this was 0.25, this was 1.5, this was 3.5, and then we said, okay, how about the volumes? This was 4.5. This was 1.571. This was negative 0.393. This was negative 0.393. So then multiply row by row. 10.125, 0.393, negative 0.589. By the way, what software package would make quick work of this? There we go. And then sum at the bottom. We'll sum up the volumes. We'll sum up the volume times the moment arms. And so therefore, and we get a Z bar of something like 1.618 inches. And the point is, if you wanted to do one for X bar or Y bar, ooh, I didn't put a bar over it. It wouldn't be really that challenging. It would just be sort of the same stuff all over again. Okay. Does that make sense? Okay. Any questions? Okay. All right, so I've given you a problem on this. That'll be due Friday. Again, I don't think the homework is longer. I'm giving you the day off Wednesday. So, okay, can I go back to the slideshow, or is anybody still writing? All right. Okay. So, all right. So in terms of centroids, that's all I have to teach you, okay? Because we've done centroids of areas, we've done centroids of lines, of volumes. That's pretty much it when it comes to centroids. So why do I have two more lectures, or this and then the lecture next time? Why is it still titled centroids? Because we're going to do something else. I want to talk about another term related to a shape, and that term is called the moment of inertia. Okay? One question that's worth posing at this point is, what does the moment of inertia have to do with the material that we've discussed in Engineering 213? And to be totally honest with you, nothing. Not a thing. So some of you are probably asking, okay, then why are we talking about this? Okay, two reasons. Okay, the first reason is that the moment of inertia is an incredibly important section property that will be relevant to every single one of you later on in your engineering curriculum. Okay, the second reason is that in order to compute a moment of inertia, you must be able to locate the centroid. And in fact, the algorithm that we use to locate and to compute the moment of inertia, we can just sort of tack it on to a centroid calculation. So it's a very natural place to go ahead and start learning about it. So this is kind of a good point to talk about. Now, in order to explain what I'm talking about and explain where a moment of inertia is relevant, I want to go back to something when we were first deriving our calculus-based expression for centroids and whatnot. We had a notation that we had developed, and we said, okay, we have the area, and the area is just the integral of dA. We're just summing up those little dAs across our region of interest. And then we have the first moment of area, which was the integral of x dA, right? Now, was this useful to us? Yes, it was useful because we took that and divided it by that, and we got x bar, right? That's how we derived x bar. Well, this is the first moment of area. The second moment of area would just be the integral of x squared. Okay? So we could have an x cubed, an x fourth, an x fifth. So if we had the integral of x to the seventh dA, that would be the seventh moment of area. Okay? Do we talk about the seventh moment of area in engineering? No. Because it's not useful. Okay? The first moment of area is useful because that's how we located the centroid. The second moment of area is useful because it has a very particular use in engineering. In fact, we don't even call it the second moment of area. We call it the moment of inertia. Okay? It has a very profound impact on response. So let me give you a visceral example to explain what I'm talking about. Let's say, how many of you all have, like, at your house have like a deck or a porch, like an elevated porch, maybe something about like this, okay? So if you were to strip out the little slats that the grill sits on and the benches sit on and so on and so forth, you're gonna find floorboards that are sort of oriented like this, right? They're sort of sticking upright, okay? Why aren't they laying flat? Like, why do we do this and not that? Why? Now, before all the math, before all this mathematical discussion, the answer you would have told me is, well, they're just stronger that way, right? I mean, imagine taking a yardstick. If you have a yardstick, one way that you bend it, it's really flimsy, right? But then take the yardstick and turn it 90 degrees and suddenly it's really like stiff, right? If you were to whack somebody on the head with the yardstick the stiff way, that would really hurt, right? Make sense? Okay, now that's just the common sense answer. Now let me give you an engineering mathematical description. I propose that if you were to compute the moment of inertia about the horizontal axis of this shape versus this shape, you would get a much larger value this way than you would this way. Make sense? And that's what a moment of inertia is. A moment of inertia will tell you flexural response. If you're going to take something and bend it, okay, what is the most opportune way to bend it? There are a number of reasons where this would be applicable in both civil engineering and mechanical engineering. I'll give you a biomedical engineering example. Let's say you were to take the cross-section of, say, a femur and compute the moment of inertia about various axes. Whichever orientation gives you the lowest moment of inertia is the way that bone would break, most likely. Does that make sense? So just, you know, this has profound impact in any field you could think of. Okay? Now the way that you compute a moment of inertia is you take the integral of x squared dA. Okay? So just to walk you through the calculus of how this works, let's go back to this example. We had done this example in a calculus fashion, and I'm going to walk through the math very, very quickly. I'm not going to do this problem over and over again. And by the way, I'm not going to make you all on a homework assignment or even on an exam locate or compute a moment of inertia using a calculus-based approach. What we're going to do on our homework and maybe on our exam is use what's called the parallel axis theorem. We're not going to talk about the parallel axis theorem until Friday. But just to sort of make the point, if you're using a calculus-based approach, the calculation isn't really that challenging at all. So let's take this region. We had done this problem in class. We said let's locate the centroid of this region. Now I want to compute the moment of inertia. So I put my little cheat sheet here on the board. Let me just remind you all of a couple things that we've already done with this example. Okay? So I'm going to make a point about a couple things. Okay? Let's recall. Okay? Recall that one of the first things that we had done for this example is we had derived dA. Okay? Now for dA, we had two definitions for it. We had x squared dx, okay? And then when we performed our integration, we integrated from 0 to 3 when we did it this way, okay? So, you know, integrated this way from 0 to 3. But if we integrated up and down, another way was to say this. And then we integrated from 0 to 9. We've already done this. We had already did this in our last example. Okay, we already did this. Okay. We've already computed the area which is 9. We already did that. Okay? And we had already done these integrals. We did qx and qy. Qx and qy are our first moments of area. And our first moments of area were just the integral of x dA and the integral of y dA. Oh, here I made a rookie mistake. I forgot to flip the indices. Remember that the first moment of area about the x-axis is the integral of y dA, and then the first moment of area about the y-axis is the integral of x dA. We had already discussed that as well. And when we did that, we got an integral of 243 over 10, and then 81 over 4. So all I'm going to do is the following. All I'm going to do for, let's say, the moment of inertia about the x-axis, the only way that it's really easy. Instead of integrating y dA, I just integrate y squared dA. Okay? And so that's just going to be the integral of y squared dy. Oh, I had a typo up here. That's not dx, that's dy. Whoopsie. And then I'm going to integrate that from y equals 0 to y equals 9. And again, I don't think that this is all that challenging because we've already done integrals like this before. And so I'll go ahead and tell you, when you chug this out, you get an integral of about 243 over 5, or 48.6. And then, or sorry, nope, I got that backwards. Man, I think my coffee wore off. This is 729 over 7. This one's 104.14. It's the other one that's 48.6. So this one's just integrating in terms of x. And so there we go. The main point I want to make is that here's the shape. Okay, so let me sort of draw the shape. Here's the shape. And so imagine that I had a, let's say, I don't know, like a prism made out of this shape. Let's say I had a prism made out of this. About which direction would it be stiffer? Bending it this way or bending it this way? Okay, and I propose that if we look at our shape, it would be easier to bend it sort of this way than it would to be to bend it up and down. Okay? And that is reflected by the fact that the moment of inertia about the x-axis is higher than the moment of inertia about the y-axis. It's kind of like I said about the floor beams in your deck. Oriented this way, the moment of inertia is higher than if they are oriented this way. And so what we're going to talk about on Friday is how to compute the moment of inertia of a composite shape. Okay, again, we're not really going to do the calculus, but yeah.
So if this is in real life, how would you know what like x squared would be? Like how would you know what the curve would be?
So that's a good question. Are you talking about the shape?
Yeah.
So I'm going to give you a couple answers. So in real life, okay, to be honest, we're not really going to have many like steel I-beams or even the femur that I mentioned earlier. We're not really going to have them mapped by like an x squared or one, square root of x or something like that. This is just for us to wrap our head around the map. In real life, one of two things is going to happen. It's either going to be comprised of simple shapes like rectangles, triangles, which is what we're going to do, or the shape is going to be highly irregular, in which case you would just get a software program to calculate it anyways. And what is that software program going to do? It's going to break it up into a bunch of tiny regions and then basically do it that way, sort of a pixel by pixel basis. Like there's image correlation stuff that'll do that. Sound good? Don't worry. Let's revisit that on Friday. Sound good? All right, I'm going to pull up the code one more time. I will see you all on Friday. Draw that line there.